The apparatus that we use to measure pressure will be a bottle, and you've seen this on the experiments tape, but we have a bottle with a tube and a stopper in the top of the bottle. The tube is tightly fit into the stopper so air can't enter or escape the bottle. The tube comes down and makes a U, and then it goes up to a sealed end. Down in the bottom of the U we have some alcohol, some colored alcohol. Now we use alcohol instead of water because water, with its surface tension and so forth, doesn't move through the tube very well, and we end up with bubbles that are difficult to get rid of. The surface tension of the water prevents it from flowing together, and we have difficulties with water. We have the alcohol up to some level. If the inside of the tube is at the level of is at air pressure, then the level here will equal the level out here. That is, if we're at atmospheric pressure, whatever the pressure is. Let me back up. If the bottle's at atmospheric pressure and the air in here is at atmospheric pressure, then the two ends of the alcohol will be at an equal level. Otherwise, they won't be at an equal level. Now, if we're to heat up the water, if we're to heat up the bottle and heat up the air in the bottle, let's say as we do in the experiment by immersing the bottle in either hot water or ice water, then the pressure in the bottle is going to either increase or decrease, and we're going to be able to see how that happens. It's very clear here. If the pressure increases, there's an air column between here, and this end is sealed. There's going to be more pressure in this air column. We're familiar with the idea that more air pressure will compress a column of air. And that's exactly what happens. The alcohol moves up in the column if we increase the pressure. If we cool the thing off, if we cool the air in the bottle off significantly below air room temperature, whatever temperature we had when this thing was at atmospheric pressure, then the length of the air column will increase. We're going to be expanding the air column. And this makes a very good experiment, very good demonstration. It's not as accurate as I would like, but we still can get the idea of the gas thermometer, and we can consider why the experiment doesn't work perfectly. Now, the pressure is, it turns out, inversely proportional to the length of the air column. So that if we have, let's say, an air column of length 30.1 centimeters at 60 degrees Celsius, this is point B, a pressure of 39.5 in ice, this is at point A, and these are readings that we actually got in class, then the pressure at B divided by the pressure at A is going to equal the length of the column A divided by the length of the column B. That's the way inverse proportions work. The ratio of pressures will be the inverse of the ratio of the lengths, so that a greater length means a lesser pressure. And that's something you should be familiar with from your mathematics and from your study of science. So that in any case, the pressure at B is going to be 39.5 over 30.1 times the pressure at A, and that is approximately 1.32. It's not just 1.32, it's 1.32 times the pressure at A. So we have a ratio of 1.32 between the 0 Celsius ice water temperature and the 60 degree room temperature. Turns out that that's not exactly what we would expect, but we're going to use it anyway. And what we're going to use it for is to make a graph of pressure versus temperature. Now, pressure and temperature ideally and theoretically should be related by a straight line. As a matter of fact, this is how we define temperature. We define it as a straight line graph that you get with an ideal gas. Now, as your text tells you, air is not an ideal gas, but it's fairly close, and most of the error in this experiment is not due to the fact that we don't have an ideal gas. It's due to the fact that we're using a plastic bottle which compresses a little bit under pressure and other imperfections in the apparatus. In any case, at 0 Celsius we have what I'm going to call 1 unit of pressure. And at 60 Celsius we have 1.32 units of pressure. We don't care what this unit of pressure is. We don't have to measure it in pascals or atmospheres or pounds per square inch or any other specific unit. It's just whatever the pressure is at A. And the pressure at B is going to be 1.32 times that. Okay? The pressure at 60 Celsius we observed to be 1.32 times the pressure at 0. We extrapolate our two data points linearly to find out where the pressure is going to be 0. Where's the pressure going to reach 0? And that's going to be our definition of absolute 0. Now our definition is absolute 0 is the temperature at which pressure reaches 0 for an ideal gas. Not for air, which is what we're using here, but for an ideal gas. So if this experiment was done with very accurate apparatus and an ideal gas, we would, just from these two data points, we should get a pretty good idea of absolute 0. Of course, what we would actually do is do a lot of data points and get a real good idea of absolute 0. Okay, to determine this temperature, we use similar triangles. We have a triangle here, we have a triangle here, and these triangles are similar because of the straightness of this line, and this line's parallel to this line, and so forth, and that should be obvious to you. So that the proportion this side over this side should equal this side over this side. Well, this side I've designated by question marks. We say question mark over 1, that's this side over this side, equals 60 over 0.32, this side over this side, and we get 1.87 Celsius here. And of course, since question mark divided by 1 is 187 Celsius, we determine that this distance is 187 Celsius, and that absolute 0 lies 187 degrees over on this side. Now really it's 273 degrees over on this side, so we only got about 2/3 of it, again because of imperfections in experimental technique, imperfections in the apparatus, and so forth.